thanks everybody for joining. It's actually kind of surprising. I thought today would be I was gonna have to apologize and say, sorry that there is nobody here to hear your great talk. Being that it's the last day of classes and everybody has nothing else to do today, or the next couple of days. Yeah. But also fitting that today being the last day and we're about to have a break, we're getting some fun snowflakes from outside. Well, that was quite nice of the weather to coordinate that with us. But otherwise, I won't take up too much more time. But today we have Dr. Scott England, who's a professor in the aerospace and ocean engineering department. As probably many of you know, but here to talk to us about ionospheric observations from formation flying spacecraft.
All right, thanks, Kevin. So I tried to come up with a provocative title to get people to show up. It worked. I don't think this is technically formation flying, but let's pass by. It's near. We'll get into it in a minute. So we're going to be looking at what we can do with a couple of spacecraft flying, let's say, close to each other. This animation is one day of the stuff that we'll be looking at. See the colors. These two spacecraft are not exactly in the same orbit plane, but they're close enough. They get slightly different periods by a few minutes. So over the course of this day, you'll see at the start of the day, right, Cosmic is tailing Icon with nearly the same ground track, just flying a little bit behind it. You can see at this point it's about to catch. There'll be a little time when they're kind of right on top of each other. We'll get into details in a minute, but to give perspective, they're about 50 kilometers different height. And then for the rest of the day, Cosmic will be just a tad ahead. It goes around. There you go, it's passed ahead. So we will cover a few things. Oh, no, there. All right. I have a couple of slides on the system we're looking at. So this is low latitude ionosphere, to give you a preview of what we're looking at with the observations, then a little bit about making multi-satellite observations in situ. The instrument we're going to use, the days we're going to focus on, and then we'll get into the comparisons. And the good stuff is all in item 6. Okay, low latitude ionosphere. So it's intended as at least a reminder for everyone who took my class and forgot everything I taught. We break up the ionosphere into different layers by height. Imaginatively give these names of D, E, and F, based mostly on composition changes, but also density changes. So the figure on the left gives you a simplified view. The specific thing of being low latitudes is shown on the right. That's showing the magnetic field in this region. So we're mostly going to be looking between about plus minus 20, a couple, maybe plus minus 30 degrees off the magnetic equator. If we look at looking forwards, the altitudes we're going to look at with the spacecraft flying, they're going to be flying between 500 and 600 kilometers altitude. In terms of the ionosphere, that's the F region. You can see it on the left, you can see it on the right. So we're up near the top of that wonderfully green shaded box. That does not show up on the projector here because it doesn't do green. So we're up near the top end of that box. When we're near the magnetic equator, the magnetic field is almost exactly horizontal. As we get off it, it starts to incline at roughly twice our latitude. So if we're 10 degrees latitude, it's inclined at about 20 degrees to horizontal. But this region here is very different from looking at mid and high latitudes where the magnetic field lines kind of point straight out of the Earth going off out into space. This is a contained. Oh dear. What are you doing? There we go. All right. So some of the features some of the phenomena that happen in this region. One of them is the wind-driven dynamo. So we have neutral winds blowing in this region at low latitudes. they can collide with the ions, more so than the electrons in the E region. We can end up with a system where we're basically taking mechanical energy from the wind, converting it into a current. So here, ions moving. In regions where conductivity's got gradients or the winds have gradients, we'll get divergence, leads to electric fields. So we can have electrostatic fields in the presence of a magnetic field, which from plasma courses can lead to an E cross B motion, so a motion of both the ions and electrons perpendicular to both the electric and magnetic fields. And that will happen anywhere along that field line. So what happens up in the F region is ions are being produced near the equator, and during the daytime, this wind-driven dynamo tends to lift the ions up. By up, it's perpendicular to B, so exactly up at the equator, slightly up, and to higher latitudes everywhere else. It does a couple of things. Lift ions up in altitude, you kind of remove their ability to collide with molecular neutrals and charge exchange. So it increases their lifetime a lot. It also sort of builds up a bunch of plasma either side of the magnetic equator that we call the equatorial ionospheric anomaly, or EIA. Over here, some ground-based measurements of that upward movement of ions taken at the magnetic equator. And here's sort of a 3D visualization of what this EIA looks like if I use a model. This is sort of late afternoon here. All right. Another phenomena that's going to be important later. We have another portion of this wind-driven current system. This is the F region dynamo, so another wind-driven dynamo that really sort of has its time in the sun. Boom, boom. At sunset. So what happens at sunset specifically? This is a plot of conductivity versus height. You can ignore the direct conductivity, but the Hall and Pedersen, the ones that act perpendicular to the magnetic field, are really high in the E region by day, and then at night, these conductivities drop by many orders of magnitude, which sort of acts like you can no longer flow current through the E region to zeroth approximation. This transition is happening right around sunset, so the E region recombines really fast. When that happens, there's then a geometrically complicated situation with before and after sunset and function of altitude and stuff that leads to this pretty strong upward motion through E cross B that only happens right there near sunset. This moves the ions even higher in altitude. It also can kick off or help to kick off a plasma instability that we find in this region. That's sort of a magnetized version of Rayleigh-Taylor. When you see the features generated by the instability here, they're seen as these sort of dark patches in the EIA. They can get referred to as plasma bubbles. So this is voids in plasma, air in the plasma, hence bubble. Different terms. I'm going to try and use plasma bubble here. All right. So that's some of the stuff we know we're looking for. I want to make measurements. How can I make measurements of this region? There's a few ways. There are more than I listed here, but I listed three broad categories, right? I can make in situ measurements. I can make remote measurements looking straight down, or NADA, and remote measurements looking at the horizon or at limb. I'm limiting myself here to spacecraft observations. I can do a lot of other types from the ground. All right, in situ, big strength is I can measure really small spatial scales, scales that I cannot see with these remote measurements. I can measure some quantities that are hard to measure remotely. So an example we're going to show later is ion temperature. It's hard to get with remote measurements from spacecraft. I can do it with an ISR, but I only have a couple of those to work with. So, right, big weakness of in situ though is if I'm on a moving platform and I have one measurement, making a point measurement, I cannot separate spatial and temporal variations. I'm going to overcome this by having more than one platform. previewing where we're going. Remote, if I look straight down, I can get high spatial resolution. Depending on my vantage point, I might actually be able to separate the spatial and temporal changes. And looking down, I can get information from way below the spacecraft, right? Below where I can fly, like the region. But big weaknesses, usually no altitude information straight down, or at least I've averaged across a bunch of altitudes, which is going to limit the vertical spatial information. And then if I look on the limb, I can get altitude resolved information, usually at really low horizontal resolution. And anytime that I've got strong horizontal gradients, like near the EIA or where I've got these plasma bubbles, limb measurements are pretty bad. If I back up a second, if I look at one of these, this is an optical signature. If I look at one of these features where it's going bright, dark, bright, if I look at it this way on the limb, I would see it perfectly. If I looked at the same feature looking this way, I'd have no idea it's there. And odds are I'm probably looking at some angle not perfectly along the magnetic field. So all of the strengths, in situ's got a big weakness. We can overcome it. We've known this for a while, by just flying more spacecraft, right? Give me more money, build you more spacecraft. So a good example of this is Swarm, shown on the right. Swarm has a few missions. One of them is to try and see magma flow and stuff inside the Earth, magnetic field inside the Earth, but it does ionospheric measurements too. And it's 3 spacecraft. There's 2 that are always close to each other here, one that's at a higher altitude, and so it, as a function of time, its plane kind of drifts. It's in a near polar orbit. It does great stuff. Another example shown over here, this is from a study this year using the Cosmic 2 constellation, so 6 spacecraft, and then also Icon. So in this, I've got to get this right. I think Icon is maybe this one, and these others are various Cosmic 2 spacecraft. And over this region in sort of Southeast Asia, out over the Indian Ocean and Pacific, we start to get, they can intersect these plasma bubbles, and taking these different lines between them, they can make some spatial inference from what's going on. All right, instrument we're going to use today. So become apparent in a minute. We're going to use something called IVM instrument, or ion velocity meter is what it stands for. It's really 2 sensors held in one package. You can see it here. One on the top that looks like it has a round entrance is a retarding potential analyzer. So this uses an applied electrostatic potential to slow down incoming ions. So this is on the front of a spacecraft flying forwards. I apply a field, I can slow down the incoming ions, measure a current behind it, and I can get curves like this at the bottom. So as a function of how much potential I apply, I see the current coming in. Total current coming in tells me about the ions are there. As I start to apply a bit of retarding potential, I stop all the H plus pretty quickly. And then at a higher potential, I start to stop the O plus. So I can get things like O plus to H plus ratio. If I assume the ionosphere is made of 2 ions, this is flawless. You can see the O plus does not stop all at exactly 1 voltage. That spread gives you a measure of temperature. And you also have this particular center point gives you a measure of how fast the ions are moving towards the spacecraft. The other sensor down here labeled IDM looks like a little square. That's 4 sensors, and it basically just measures 4 currents to get a rival angle. So this thing's really simple. It's about 15 inches tall. I used to be bigger. Why is this useful? So this instrument's been flown a bunch, and for a time, there was 7 of these flying in relatively similar orbits. It's 8. Something than just this. There was 2 on Icon, 1 on each face. So whether Icon flew forwards or backwards, this sensor would be pointing towards the incoming ions. Icon was in a 27-degree inclination at about 600 kilometers altitude. Then there's 6 more on the Cosmic 2 spacecraft. The instruments are essentially identical. There's a couple of resistors and things that are different, but they're essentially as close to identical copies of each other as you can get. Cosmic 2, for the times we're looking at here, we're operating at about 550 kilometers, so just below Icon, at 24-degree inclination, which is close to 27. All right. So what lets us do all of this? The cosmic spacecraft space themselves out to get their global coverage in their constellation. Icon's flying along, and there's this time period that we found where it yields that movie we started with, where the planes are nearly aligned. So I won't go into all the orbital mechanics of this, but the planes drift around in inertial space. If I assume 27 is 24 for a minute, right? They're both drifting at different rates. There'll be a time when these sort of line up like this. There's one of these lineups in early 2020 between one of the Cosmic 2 spacecraft, it's Cosmic 2-4, and Icon. So the planes kind of align. But then the other important thing is that not just the planes are aligned, but the 2 spacecraft are about in the same place in those planes. You could do other stuff if one's in the day and one's at night, but we're trying to find times when they're real close. We looked through a whole bunch of this to find times where they pass within 2 degrees long within a 5-minute time period. So we define that as a conjunction. Then we look for where this lasts for a bunch of time. So, I mean, 2 ships, passing in the night, they could cross each other at 90 degrees, right? And meet this criteria for 2 seconds and then never again, right? We're looking for where they hold this requirement for at least 10 minutes. 10 minutes, they're about 90-minute period orbits. This is a big arc of an orbit. And there's this time in sort of March to early April of 2020 where this just starts happening all the time. After that point, this doesn't happen again. So what's happening here is I basically have 2 runners on the track doing laps, and they're going at almost exactly the same rate, but one of them's ever so slightly faster. So when they're close, they stay close for lap after lap after lap, but when one gets ahead, it's an awfully long time before they've fully lapped the other runner. And the next time this happens is 2 years later or something. And at least when I started this study, that data wasn't public. So I did what I could. So we zero in on a 2-week period. I just look, basically, this is just looking at ion densities measured by the 2 instruments for that 2-week period. Here's plots at the top. These axes on the bottom, this is time of day, so noon in the middle, midnight. And this is the ion density, and then the color coding shows how many 1-second samples fall into that. Right. And generally, it's sort of what you expect. Higher density in the day, at night, slightly higher density seen by Cosmic, it's slightly lower than Icon. Generally pretty good for green. You'd hope they're the same instrument, at the same time. Anyway, I can go ahead and just plot the instantaneous points against each other and get pretty good correlation. This is moment by moment whenever they're close. Yeah, R squared of 0.95. The 2 instruments are pretty similar, is the conclusion. I can then take all those long conjunctions, the ones lasting more than 10 minutes, and they're shown at the bottom, and I've separated those into what's happening during the day versus night, with some arbitrary cutoff for the ones that passed over the terminator. And the color coding shows the correlation coefficient between the 2, just for that 10-minute segment. And generally, you can't see anything through the projector. But during the day, they're all really high, and at night, they're not. And why that might be, could be a number of reasons. One is the measurements are getting, the density is getting really low at night, and the noise, the signal to noise is dropping. The other thing is there's those plasma bubbles at night, which gives me small scale structuring that one could fly through it while the other one totally misses it. So if I'm just looking second by second at the correlation, I may not see what I'm expecting. So it passes the basic smell test. Let's go look at it's beautiful on my screen. Let's go look at a really basic feature of the equatorial anomaly, the EIA. So on the left, this is the actual pass. So at this point, they fall within that 2 degree, 5 minutes of time. Out here is where they leave it. They actually pass right overhead, you know, somewhere here over the south, I guess just south of the equator. The color contours here come from an oscillative model that is trying to say what the ion density at this height would be. And it predicts, you know, one peak in the north, bigger peak in the south of us flying through them like that. This is what the two spacecraft see. It all lines up perfectly. So when I go looking for the most vanilla stuff where I know the answer, it all works. In theory, there's a point in here where the two spacecraft are kind of right above each other and I could get out scale heights and try and infer some other stuff. But that wasn't interesting. So I moved on to what was. So here's a fun one. And yeah, we're gonna have to, you'll have to believe me. Top left plot, okay, there's the conjunction. It's out over the Pacific. Okay. Let's look at the bottom two plots for the minute. So this plot here is showing the density measured. Red is cosmic, blue is icon. The scale doesn't start at 0. Okay. So cosmic's measuring a bit higher as they fly. So they see similar features, right? There's some oscillations here, but which we're going to get back to in a minute. And then when we pass just a little after 180 degrees longitude, we get this feature. And it's it's about 19 consecutive measurements. Cosmic 2 sees the density go up from about 6.5 to a little over 7.5 times 10 to the 4 per centimeter cubed. So, you know, like 20% enhancement in density. About 1.8 degrees wide. Icon flies through this region about 5 minutes later. So while Cosmic's making this measurement, Icon's way back over here. When Icon hits the same place, it sees a smaller bump, but there is a bump where my cursor is. And this next one's really going to request. Icon's not just measuring the densities, though, it's measuring the arrival angle of the ions. So you can see the motion here. I'm pulling out the motion perpendicular to the magnetic field, so trying to look for that vertical motion. And right here at the 180, the motion goes from being predominantly downwards, which is fairly typical for solar min. So it goes from being downwards at about 10 meters a second, upwards at 15, and then back. This is impossible to see on the projector. Maybe on the projector you can see a point out here. Yeah. It's the same width, it's the same place, right? So this uplift is, I'm going to say, is definitely related to this density enhancement. So what is causing it? Well, first thing to think of is, well, that we've got the F region dynamo, right? Where's sunset and where's my pre-reversal enhancement? So I go up here, take Icon, it's on a field line, so I trace the field line down to the E region, 150 kilometers, and I find the solar zenith angle at that point, so the angle to the sun from vertical at those points. That's shown for the north and the south with the blue and red lines here. The hard Earth cutoff, right, the Earth's shadow is shown by the green, yellow horizontal line, right? So passing sunset in the E region here. Pre-reversal enhancement should be starting maybe from around here going out a little after here. So I mark it roughly with that black line. And then I go look at the drifts. This is my pre-reverse enhancement. This measly little thing takes me from -10 back to 0. Back, right? That's what my F region dynamo is doing. And this is typical. Deep solar min, you don't see a big uplift at sunset. This feature's occurring, you know, like an hour later in local time, a few degrees away. It's way stronger and it's way narrower. And it's at, you know, really quite high solar zenith angles for the cutoff at that. So start looking around trying to think what this can be. So there is a tell here. This is happening after sunset near the magnetic. It's actually almost bang on the magnetic equator. And it's about 2 degrees wide. That looks like a plasma bubble. Except plasma bubbles are dips in density, and this is a spike in density. I'm searching back 20 years in the literature. I found this study that focused on reported spikes in the density. So they've labeled theirs A, B, C. You can see occurring just after sunset. This one's, you know, around 9 o'clock magnetic local time. And then from subsequent orbits and another spacecraft, they were able to show each one of these was associated with a plasma bubble. But there's 2 big differences here. One is they only ever saw these past 10 degrees magnetic latitude. They said they do not occur between ±10, and we're at about 0. And the other thing is they were seeing, you know, factor of 2, factor of 4 increases. We're seeing 20%. And they have a whole mechanism that's basically saying, well, look, as the bubble's forming, it's limited in latitude. And I've got these electric fields that are driving its rise. And it's just its northern and southern edge, instead of that leading to this big void rising up, it can lead to a local enhancement of the plasma density, which wouldn't work at the equator. But I think what this is we're catching a bubble during formation. So it's the top side of the top ionosphere just rising before that void comes up through it. We got real lucky, because a couple of minutes after this there would have been a giant depletion, which I can't prove because this is out in the middle of the Pacific and there's no data. All right. The last one had some wiggles, so let's go look at another one that has some wiggles. So here's, again, you see each one of these, right? There's my track. First half of this data is out over the Pacific. The second half is over South America. This panel here shows the densities and the drifts, just all compressed into one panel, versus longitude. This is them against universal time. So you can see cosmic is, I think, 4 minutes behind icon. Anyway, there's a region where we're passing over the northern portion of the EIA, then the dip, and then this is the southern portion. Within the northern portion, there are unmistakably these oscillations where it goes up, down, up, down, up, down in density. And at roughly the same place, right? Icon is seeing it go up, down, up, down, up, down, up, down. So I look at that and my mind goes, okay, I've got a wave. These get termed traveling ionospheric disturbances because we need to make more names. If I look at the drifts too, right? They have this up there and up there and up there and up there. So the drifts look like they're oscillating right on top of the densities too, right? Because again, TIDs have been seen lots of times. People can see drifts varying, people can see densities varying. There's a problem always with in situ observations of TIDs. And that is, okay, I pass through it. If I can convince myself it's a wave, I can get its amplitude, see peaks and troughs. But then I want to know its wavelength and other parameters. And the problem is, I don't know its orientation. All I have is a snap, is a line through it. There is a wave field. There's 3 spacecraft tracks through it. Every one of those sees a different wavelength, right? The green one says, what are you talking about? There is no wave. The red one, orange, sees pretty close to its true wavelength, and the yellow sees something in between. But unless I know the wave field is this, so unless I have a ground sight telling me, and I'm out of the Pacific, so forget that, I can't solve this problem. But can I? Well, I have 2 things going for me. One is the ground tracks are not straight lines, they're curved. They're not curved a lot, right? But they curve, they're going more southwards as they get further east. The second thing is I've got 2 of them, and they're separated a bit in space and a bit in time. So I look here, this is just the densities seen by each, plotted with longitude and density or latitude and density. And the vertical lines kind of mark where I see the crests. Okay. As I go from left to right on the longitude plot, those crests look to be getting closer together. The last 2 is closer than the first 2. That would work if, as I turn more southwards, I'm becoming more perpendicular to the phase frames. On the right-hand side, where I see it with latitude, it sort of does the same. So as I go to the left, they get closer. So there's a bit of a tell, but what I want to do is use the information of where I see the crests in their latitude and longitude, and the times at which I see them, and the actual flight paths through a wave field. So I generate a time-dependent wave field, shown here as one example. It happens to be the answer. And then I fly my 2 spacecraft through it. And as I go through this, following their curved trajectories at their appropriate times, I then record what I see, these mythical sign-like looking waves on the right-hand side. And I record where I find my crests versus where I actually saw them in the observations. And then I basically look for how, which I come up with a metric for how close I am, measured in degrees, right? So I've got degrees longitude difference, degrees latitude difference, 4 peaks. So there's 8 things in it, do an RMS. Okay. Then change the wavelength of this and repeat. Then change the wave azimuth of this and repeat. Change the wave period of this and repeat. I got bored at 14 million instances of the wave field, but search through that and I can find the global best fit within that. That's what's shown here. And at least you can see the vertical blue lines on the projector. So it does a pretty, not perfect, but a pretty good job of lining up. There's one of them here that lines up a bit worse. And this one here that's a little bit worse. That's the 3rd peak as we see it. This is the time-dependent field that corresponds to. So again, it's sort of consistent with our initial thought that as we go from left to right, we're turning more perpendicular to the wave field because we're turning to head more south. And that's the wave field that's moving mostly north. Kevin, you can almost see it. All right. Plasma bubbles, we can fly through them too. Here's an example of us seeing, density depletions in both spacecraft. Associated with that, you get big vertical rises. So what little plasma is there is rising up. I can zoom in on like an individual one of those and try and mark its western edge. And I can pull out some gradients to see if these things are tilted a little bit. Theory suggests they should be. That's been done before. I can see plasma bubbles, not just after sunset, but also at dawn. So these are ones that we think formed many hours before and just survived the night. And around dawn, you can see them, and then an hour or two later, production of ions basically got rid of these. Picked this pair out for interest. This is actually two consecutive orbits. So the first orbit's on the top, second's on the bottom. On the top, we see these two depletions here at around about 6 and 6:30 local time. Go one orbit later, so an hour and a half later. They are roughly, I think it's these two depletions here, and then we see a whole bunch of others. These two tracks are passing up slightly different regions, right? Which I think is why the second track picks up a lot more bubbles. It's getting closer to the magnetic equator. But you can do a little bit from, are these moving? All right. What did we do? Right, to use the strengths of what we had, I had 2 weeks of data, 2 spacecraft flying pretty close, which lets me do better stuff with the in situ and tried to get at the real properties of that traveling ionospheric disturbance, which it's been really tough with in situ measurements. And then there's this narrow feature that we still don't know what it is, but we think it's a plasma bubble. And I'm going to contend that if I can do all of that with 2 weeks of data, what would I have done if I actually had something designed for this? I don't know, but I would have had things like TIDs appearing in the data when we passed over a ground site that could have unambiguously told us its period or something. And we could test our methods. As it was, we got some interesting stuff, but kind of unlucky that most of the interesting stuff was over the oceans. Who would have guessed near the equator? All right, final slide. Just pointing out, GDC is on its way. It's going to have 6 spacecraft making in situ measurements, polar orbit, and they're doing neat stuff with pairs of triangles and things. Different phases where all the planes are close, phases where it's more like a Walker constellation.
What are they trying?
6 spacecraft, so they're flying 3 as sort of a triangle trying to hold rough shape, and then another 3 as another triangle, staggered in time, so that they would, if a triangle, I can pull out some gradients, and then if I have another one pass over a few minutes later, I can pull out if any of those gradients have changed with time. And this simple plot here changes, so change in latitude, because all the spacecraft will pass over roughly the same point for polar, and then go through a weird kind of flick in this. But I'm away from that point, very close to the pole. I can do neat things with 6 spacecraft. All right. Awesome. Questions, comments? So,
I have a question about the wave patterns that you see. Like you described it as a field notice changes in the spacecraft turning. How constant is the direction of those field lines?
Yeah. So I mean, I have to assume it's entirely a planar wave, right? Many of these TIDs are seen as plane waves. Some of them are not. Some of them are spherical wavefronts.
So it holds for most.
That's for most. Doesn't hold for all. There's not enough information to if I had 3, maybe I could actually tell you for sure, is it a planar wave or at least spherical crests.
Is that potentially space that you see, or is that?
Yeah, the spike we just don't know, and that's the only thing that looks like it in timing and size. That mechanism, if you read it will yield really big density changes and doesn't work at the equator. We're seeing them at the equator, so it's there are some modeling studies that sort of suggest that, hey, before the depletion comes up, what we see at the top is a slight rise and then collapse in densities. And maybe we just got super lucky. But these are again, like 5 minutes apart. So this feature has to have held, maybe that's the big density spike and then it's collapsing by the time I can see it, the ions are still making up. Can't prove it. If that had happened over the land or anywhere where we could have seen a few minutes later that there is a plasma bubble there, then awesome. I can look at the following orbit of data from both spacecraft, but they're at a different latitude and they just don't see anything. And it's the middle of the Pacific. It's kind of not well instrumented. Yeah.
And maybe a simple question of sort of the novelty of this. I know there's been formation missions before.
Yep.
With the Van Allen, other things like that.
Yep.
There was.
Yep.
Van Allen wasn't. What was there? There was 4.
MMS.
MMS, yes.
That's 4. Yeah. So this
But
is,
they're not. Those are more. They're not kind of regular orbits, right?
well, I mean, they're doing magnetospheric measurement. They're way further out.
Yeah.
But you are right. I
guess that's. So
I
that's
put
what
in
my
a
question is.
couple of examples here, right? So swarm is an example. Cosmic 2 isn't per se. However, at the very start of its mission, they had 6 spacecraft pretty close. They're super close. They're in basically the same orbit, so you can't quite do what we were doing here. But as they start to spread them out, they can do more interesting stuff. They're also really high, which is just unfortunate, right? So they were at 720 initially, and the instruments were built more to operate down at 550, and the signal level at 720 is really low.
But I say that was my question. Is outside of swarms,
Well,
it's kind of the same.
sure. There's a Chinese mission, LOX, I believe it's called. It's a string of pearls. I think 6 sets. Each one has 3 spacecraft. They have Langmuir probes on them. We can't get the data. Can barely find anything out about them. There's like a conference talk in one paper, but yeah, there's probably oodles in that data set. There are some CubeSat projects that, like again, you got to have both either 2 or 3 spacecraft all work, then the data be public. So there's not many, is what I would contend. But here, I mean, IBM instrument, it's pretty easy. So it's not unthinkable to think of a pair of CubeSats, right? With just instrumented with us, just flying, maybe the same plane but separated a bit further. They have to work.
It's a journey to keep
Sure. And I have to be able to get the data, otherwise it doesn't exist.
So then these 6 are going to fly? Or would it sort of be
Oh, yeah.
when it does, then
Yes.
if you think about that, the data you got before is like just one snapshot of that whole
Yeah.
length of time. How many of those? How many times do we have to look to see if something like that happens? When this? If there's something up there happening,
Yeah.
then how many times do you get to look?
You'll-
Very simple question.
Yeah, I mean, this has a prime mission of like 3 years. There's different points in that mission. So there's 6 months or so where they're close, and you could do this kind of thing. There's another point in the mission where they're spacing them as far apart as they can. They're trying to phase different science questions at different points in the mission. But yeah, I mean, there's at least like a 6 month chunk where they're all kind of close. And if you were flying through some sort of a wave field, you could maybe see it with the first 3 and then get its evolution time with the second 3. Not, but for very large scale features, you'll see them on the next orbit, but generally, well, but these can get spaced enough that the next orbit of like this purple one kind of goes close to where that red one was in the third orbit, so you can get a little bit. But yeah, it should be an awful lot more. We're still recording, so I'm going to limit what I say about GDC. It's awesome. It's the answer to everything. I'm a team member on GDC. I'm very excited.
Any other questions? I'm not seeing anything online either. Anything else? Then certainly a round of applause. Thank you very much.
Welcome.